Welcome everybody to this next talk, Inside Android SafetyNet Attestation, Attack and Defense. First of all, I would like to see a show of hands. Who among you has already developed an Android app? That's almost everybody, I would say, something between 90 and 98% of you. And who of you has already used the SafetyNet Attestation API? Please, another show of hands. That feels more like 5 or 6. And who of you has already heard about this API before coming here today? That's more perfect. That's why you are all here, I guess. So gear up for a very informative talk by Colin Mulliner, an expert in the field of security research, and he's also the co-author of the Android Hackers Handbook. I'm very excited for his talk. Please give him a warm round of applause.
And I'm gonna dive right in. This was basically, just some, I did a bunch of like mobile security and development some years ago, wrote a bunch of guides and helped on this book, but let's get right to the talk. So what are the goals for this talk? The main goal for this talk is, of course, understanding what Android's safety net and especially the attestation API is, and actually how to really implement and deploy it. As you will see throughout the talk, it's not like that straightforward, unfortunately. And then we're just going to look at the attestation API, really what can it do for you and what can't it do for you. And I guess with most security systems or features, it's very interesting. The part what it can do is the most interesting part. And then we're going to look at some attacks and bypasses from other people and some of my own work. And the second main goal of this talk is like basically document this API, because Google's documentation is not very good, and that's like how I thought like, hey, let's talk a little bit about this. So of course, this entire system and this entire talk is about app security. And back in the day, a lot of apps did not communicate, but these days, if your app doesn't communicate, like who cares? And mostly it communicates with like an app-specific backend. And if the app and like the backend and everything works, the user is happy, everybody's happy. And if it doesn't work, everybody's unhappy, and the company will not make any money, and like they will like discontinue their service. So mobile app security is really interesting, because these days an app or like a mobile app is really just the gateway to like the backend service. And these days there's a lot of like online service which are basically mobile only, or at least mobile first. If you think about something like Snapchat, they don't even have like a website or anything. And app security is also about basically controlling data. So like displaying data, managing data by the app, and making sure somebody like is not allowed to copy out data that is like managed by the app. And altogether, basically, mobile app security is really about protecting like your service, your revenue, your brand, and hopefully your customer or like the consumer. So if you look at hacks in general, what are we looking actually at? The main part is like OS modification. Basically, on Android, we'd say like rooting. And rooting is basically just like to break the assumptions of the security model. Because if you root like your phone, you suddenly are able to like basically take content from apps that didn't want their content to be taken in the first place. And you can do this by just like reading data, or like taking screenshots, or like instrumenting the app and pulling data out of it. And of course, you can also just modify the app directly, and then you can just like change whatever the app is doing, or like what the app is enforcing. And of course, there's also network traffic, but in this talk, I'm not going to like look at network traffic at all. So if you look at rooting, what is rooting actually? It's basically regaining full control over your device, because these days any kind of phone or tablet, basically you don't have root anymore. Like you don't have full access to everything like on your computer. And with rooting, you gain like this access again. You gain access to resources. You can read and write any file and modify parts of the OS or like the software framework. And all of this rooting capabilities really highly depend on Android versions, and really newer Android versions are much more hardened due to, for example, SE/Linux policies, but I'm not going to jump into that part. So if you look at app security in the old days, what did you have? There were like basic routing checks, so apps would implement something like, hey, does system expand SU exist? If that's so, they was just checking, hey, did somebody root the file and reinstall SU? And if that was true, they would just say like, yeah, your device is likely rooted, this app is not going to work. And the same with apps, they would just like check if like a specific package is present, or they would check if like Xpose is installed, and maybe would try to detect emulators by just seeing what get device ID returns. And if it returns 0, it's often like an emulator. So that's like really the old days. In the old days, it was for the developers really easy to implement because they knew they can just like check for certain files or certain packages, and it's like really easy to implement. You don't have to be like a genius. You just have like check for this file, and then you can very easily deploy those kind of checks. But of course, for the attacker, it's easy as well because they also understand how this works. So they could just like rename some files or move files around, and then they can again abuse those applications. So modern mobile app security really works by collecting data. Basically, you have some piece of code that just like collects data and just sends it to the backend, and your backend will make the decision if a specific a specific thing happened. For example, if your device is rooted. And the idea behind it is that the attacker cannot just like patch out your app, like patch out checks on your app, because imagine if you just like do a file access check to like system bin SU, you can just like remove that and then the app will just work. But if you collect really a lot of data on the device, you really don't know what is used for what, and you basically have to fake all the data. And if you collect really a lot of data, you can't really do that. That's basically what all modern apps that have like a high demand or higher demand for security do these days. And also that is what SafetyNet Attestation will do for you. So just to go a little bit back to like Android. So in the early days, Android was very, I would say, very open. But these days, a lot of openness like went away. They have like secure boot now, and which is basically just a trust anchor. And basically, they just like are able to like tell if you like unlocked your bootloader and things like that. And of course, there's way more SE/Linux restrictions, so they have like much stricter sandboxes. And then Google added this platform security service called SafetyNet. And SafetyNet is really just a brand name for like security services on Android. They have a bunch of different services, like from verified apps to and then to like check for PHAs, which is Google's nicer term for like malware. And then you have attestation, and you have like a capture service. And SafetyNet in general is designed to like run on any Android device that has Google Play. So it's like part of Google Play services, and the nice part, it's like independent from the manufacturer. So this exists on any Android device, not only on like the Google devices. And with attestation, you can do remote device and app attestation. So, and of course, Google also heavily uses their own APIs. For example, if you ever used Android Pay and saw this nice pop-up, that meant SafetyNet actually failed to validate or attest your device or like I guess the Android Pay app, and they said like, oh yeah, you modified something. And one of the intentions, I think, behind the attestation part was they can't really control security of like other manufacturers' devices, but they wanted to support Apple Pay on them. So what did they do? They basically found a way to like measure if like your device or the device Apple Android Pay is running on, it was modified. And the nice part is they can really change SafetyNet, like the attestation part, on the fly, so you don't have to like wait for like a system software update. It like basically they can push code to the device at any point to like check for modifications. with that, they can like really fast react to, say, new routes or something without like having any like software updates being delivered to the devices. So what is actually the attestation part? It's really the attestation of the device and the specific app that called the API. That's basically all of the things people use to implement themselves. And as I said, it's like part of the Google Play services. And basically, you just call an API and validate that your app and device is like the device of the user was not modified. Unfortunately, the documentation, as I like said in the introduction, is not super detailed, and they leave a lot of things to like your interpretation, or just like you have to basically use it to like find out how this really works. So over time, it got much better, but when I started looking at it, which is by, I guess, 1.5, 2 years ago, some of the documentation was like really bad. And they add new features without really documenting them. They have like a private mailing list where they announce some stuff, but this is probably, I guess, the only piece of code actually I'm going to show. It's basically just like how you call it. So SafetyNet is part of the Google API client. And you basically just say, I want a connection to the SafetyNet API, and then you just like call it. So how does it actually work? So here in the middle, the box in the middle is basically, that's the software that's running on the phone. You have the backend, the Google Play backend, and your application's backend. So if your app doesn't have its own backend, you really can't use SafetyNet at all. And you will see in a second why that is. So basically what happens, if your app like talks to your backend for maybe wants to log in or do like some very specific operation, and then your backend will say, hey, dear application, I need you, I request you to like attest yourself. So the backend will basically send a request to its app. The app will then like call the SafetyNet Attestation API, and in this step, we actually see the attestation code on the device will inspect the device itself, so like the operating system, was it rooted, and then it will also inspect the actual application. Some minor detail, like in the call, there should be a nonce to like prevent replays. It's just like for documentation. So that's basically you. Instead of having you implement everything yourself, you can just call this API, and you will have all the work done by Google engineers to do your security configurations or security attestations. So what happens after attestation has checked your app and the device? It will send the data back to Google. Google will actually analyze it and then will determine the state of your device and your app, and actually forward the response to your app. And in order to make sure the app, because if you modify the app in this case, and if it would not be signed, you could just like tamper with like this attestation response. So this is signed. So in the backend, you should validate that signature and then validate the attestation, and then you actually know what you're dealing with. That's basically what you get back. It's really, really, really simple. Just some blobs of base64 encoding. So Google has a signature validation API, which is basically just for development purposes. But yeah, that part is actually pretty well documented. I guess they do that a lot, like SSL cert validation. But let's go look at the attestation data. So the attestation data, that's basically the main blob you get back. Everything else is just like a chain and the signature. So you see the CTS profile match, and that refers to, that's basically the core device integrity measure. And CTS refers to the Google compatibility test suite. So basically, whenever you build an Android device, you have to run this like test suite and give Google the results. And basically, what this API does, it basically collects data from your phone, and then it compares it to the data the manufacturer provided. And by this, they can determine if you modified contents of like your system file system. And then you see like which APK called the API, and then you get a digest of the APK itself. You get your non-spec, and then you also have like timestamps. And the basic integrity is an indicator about routing. So this is this nice table was actually only, I guess, probably added to like their documentation maybe like 7 months ago. And before it was like, yeah, there's a true and false field, and yeah. So basically here you can see CTS will only be true if your device is like genuine and passed, like the CTS data corresponds to the data that was collected. If as soon as you unlock your bootloader, that goes to false, but basic integrity will still be there. So if you just unlock your bootloader, but didn't modify actually the content of your file systems, your basic integrity is true. And that's basically those two different indicators will basically help you to understand the state of the device. And with this nice table, you can do some, basically implement like your checks. So I wrote this like small demo, like I actually implemented that for like a bigger company, but I also built this like small demo up, which I'm going to show you at the end. And you see some, it will basically just like run this attestation, and it will tell you like if your device is rooted and what the app integrity is. And you see the blob of data below, and you see like everything is it passes all of the checks, and we're going to have some more fun with this later. Yeah, the big issue with SafetyNet and the Attestation API is like error message or like error states. There's a ton of different errors, and if you don't know what you're dealing with, you can basically very easily bypass the entire system. If you as an implementer aren't aware of like error messages. So for example, this is one of the nice basic errors. Basically, if for some reason the API ran or the API call actually worked, but somehow the code inside the API like just like encountered some random error, you will get this. And they basically say, oh yeah, we just like have this like random error message, and you're then you're gonna find out like how this actually looks like, because this is not really documented. And this error basically just means just call the API again and try again. Most of the time it will just like go. This is one of the more interesting errors. This basically says we can't really determine which APK called the API. Also, they kind of think the device is generally untrusted, so they just like removed a bunch of fields from this JSON response, which is also very confusing if you like implement this the first time, because you suddenly get like broken data blobs back. And of course, this was like not really documented. So now you know, like basically, we have this API, and like there maybe the JSON field looks strange. So basically, now you can go and just like implement your app and have the interaction between your app and your backend, and your app running the attestation. But unfortunately, it's like still not that simple. So also, all of the API calls can kind of fail, and they actually will fail in the wild. Like all of every API you call will actually fail at some point if you, depending on like your user group. If you're playing at home with one of your devices, you will never see any of those errors. But if you like say run, if your app runs on like 100,000 or millions of devices, you will see every error eventually. When you have things like, like Google Play Services doesn't support SafetyNet yet, so what should you do? And one part is you can like just force a user to update their Play services, and then there's like just like general error, connection errors, and in those cases you just like really have to retry. If you forget to like handle one of those errors, that either means some client will basically not work on your network, or some client will be allowed to like connect to your service even if it was tampered with. And like the lower three cases, that's like really something you should actually be able to see during development. Because if your nonce is too short, it will actually just like fail. Even it will just like directly fail. Yeah, some more examples. So I just like uninstalled the all play services updates on this like Nexus 7, which is like an Android 4, which also doesn't have secure boot. And then if you like just start the application, you'll just like nothing will work, like because you really need to upload those play services. So a lot of the API failure things are basically temporary failures. So you basically have to start with retrying everything. Generic errors, networking errors. And in general, you should be like a good citizen and like basically do an exponential backoff after each failed try. Also, you can look into this JSON field or this JSON blob on the device itself, and then determine if you want to do a retry, then you don't have to do a full round trip to your backend. But basically, what you really need to do is report any of the failures to your backend, and really plan what you're going to do if like some device keeps just like throwing errors, because that's, in the worst case, a customer or a user of your app that can never use the app because if they have some random error. So you have to be like we have to really think hard about what you're going to do. Unfortunately, this of course is an app-specific behavior, because in some cases like maybe we're just gonna like let the person use it like once or twice, but maybe you say like we never want anybody who fails this to ever use our service. And this is like really more app-specific decisions. So let's look at so the first and the main function, or one of the two functionalities, like the OS and device integrity check, and that's basically just like those two fields which give you like true or false. But app integrity works a little bit different, because Google can't really tell you if your app integrity is there. And you have those two fields, the APK digest and the APK cert digest. And the cert digest is really like the digest of the key you assigned your APK with. So in the easy mode, so if you resign an application, the cert digest will be, of course, different. So if somebody uses APK tool on your app, modifies the app, reinstalls it, the APK cert digest will be different. So the most easy check to check for app integrity is basically just like compare the APK cert digest. And you kind of say if you have 5 different apps, and most likely they will all be signed with the same cert. You basically only have to like hard code this like cert digest into your backend once, and you can just like always compare that. That's like really, if you like done this, like it's basically a very simple comparison. But with that, you can know if like your app is like not tampered with. But you can also go into advanced mode and basically also compare the APK digest. With that, of course, a little bit different, or a little bit more difficult, because that means for every single APK you ever released to the App Store, you basically have to record the digest of the file, because if you didn't do that, you will just like reject people and say like, hey, we don't recognize this app. You probably modified your app, but in reality, maybe you just like forgot to like collect the data. So you have to have like very tight control over your release process, but you can do cool stuff like revoke specific APK versions at this like very early part in the communication with your server by just like deleting that specific digest from your database, and then SafetyNet will basically block this APK for you. So basically, so to do the implementation and deployment, on the client side, you really have to check for error conditions, retry, and report failure codes. In the back end, you really have to make sure to validate the signature and the attestation data, check really all fields, timestamps, nonce, and really make a decision about failures and what you want to do. And especially like things like, do we want to force users to update their play services, and maybe have something like a whitelisting mechanism where you can whitelist maybe specific kind of devices, because you will run into problems and you probably don't want to prevent like a specific user group from not being able to use your service. So so that's basically the part about what is a SafetyNet attestation, how does it work, what you should look out for when trying to implement and deploy it. But of course, as I guess anybody who's like interested in security, and if you like implement or a new security system, you really want to know if you can actually trust that system or if it just like does nothing. So when I first looked at it, I was like, let's see how good this actually is, and can we do like bypasses, and also what are the limitations. Obvious limitations, I guess, were different Android versions, because on Android 4 and 5 you really don't have like this secure boot state. Like applications cannot determine the boot state. So anything that would be based on unlocking your bootloader would basically work, because if you can't detect that the bootloader was unlocked, you can't block unlocked bootloader. Yeah, and on Android 6, yeah, of course you can detect the boot state, and then you can actually rely on everything that is based on the secure boot mode. But this, of course, already shows you that all devices kind of are very much harder to like judge in terms of the attestation system, because of certain limitations of the actual OS. So in your security policy in your backend, you basically have to know that, hey, if something like Android 4 or 5 devices, we might not be able to see certain things if you just use SafetyNet. And you have like other things with Android 4, so you don't have DM-verity. That means you can just remount and write or change files on the system partition. So like you can do fun things like change or rename or move like system xbin.su to some other directory, and then if you just like run your SafetyNet enabled application, you will totally bypass, or you will not bypass, but you will just pass the attestation, because the system will say, yeah, fine, nothing was modified, and then after using that app, you can basically restore SU to like by copying it back. You could also, and that also is like another basically indicator what you should do. If you only like basically run SafetyNet on app startup, you can do things like that. But say if you use it more often, like at random intervals, just the backend server is like at random intervals just like says, hey, can you rerun this attestation for me? Those things have become a little bit harder. Of course, none of this like is documented at all. So this like small demo application again. It's like this was like a Nexus 5 X with Android 6, and I just unlocked the bootloader, and then if you like run the attestation, we'll see something like this, like secure boot mode. That actually doesn't come from the attestation API. I just like read that from the system properties, but it basically detects unlocked bootloader, and so it will change where is it? Yeah, the CTS profile in the middle to false, and it would also give you like an advice where it's like, hey, you should relock your bootloader. And this advice field is also something that just like added, I think earlier this year, they just added it, and I was looking at this JSON file, and it was like, hey, there's a new field, and it's like undocumented. Nice. So, SuHide and Magisk. So, obviously, if a system like that exists, people will try to bypass it. And one of the first bypasses for this was SuHide. Basically, it's you can call it a rootkit, because it's really just hiding, trying to hide basically that you rooted your device from SafetyNet. And that was the SuHide was very simple, and Google very easily actually detected it. And you could actually read in forums like the people would post, "Oh, I can't like use SuHide anymore." They did now detect that, and like 2 weeks later, it was like, or maybe even like 2 days later, there was like an update, and it worked again, and then it was like detect it again. And that's really where this like short iteration cycle due to like code pushing comes into play, where Google can just like really fast react to whatever changes there are. And then Suhide was discontinued because the guy basically said like, oh, I give up, like they can like change their detection so fast, and I want to do something else with my life than just like updating. But then there's Magisk, which is yeah, a more modern way of like basically hiding root. But Magisk is based on unlocking the bootloader and patching as a Linux policies and so on. Actually, this is, as far as I know, completely undetectable at the moment due to SafetyNet actually not running with full system privileges. Yeah, in this phase, you really have to like unlock and modify, or like unlock your bootloader and do like heavy modifications. So it's like not probably done by a lot of users. But yeah, basically all those tools are basically real rootkits to like hide root from security services on Android. And yeah, Google is playing a nice cat and mouse game. So yeah, and also those two basically just try to hide system modifications or routing, which is only one aspect of SafetyNet, or the SafetyNet Attestation API. So I was more interested in app integrity. Yeah, because yeah, the other two like checks can obviously be bypassed, and really nobody ever looked at app integrity, and I was really wondering why. And I was like, yeah, that's kind of interesting for us. So I was looking into app integrity. And basically, the goal behind app integrity is like really to detect if somebody modified your application, and you do that by looking at the APK digest and the cert digest. Because if you could modify the APK, you can do something like remove like the TLS cert pinning and like modify traffic and things like that. And you probably don't want that to happen. So that app integrity is like very interesting. So well, how does app integrity, or how does like the cert digests actually work, or the APK digest? The interesting part is those two values are calculated on the APK file that is stored on disk. But if you know how Android actually works, you know like Android doesn't actually execute the APK. Because APKs contain DEX files, and like until Android 4, DEX files would be converted to ODEX, like optimized DEX files, which is like a bytecode. In Android 4 and 5 and later would just like compile the DEX code to native code. And there was 3 years ago, there was like some work done on patching ODEX files. So this like problem of calculating checksums on or digests on one file, but executing another file can, I would say, obviously be attacked. So if you like rehash the code running again, so on Android 4 and 5, you basically have the data directory, and you have under data you have app where your like APK sits, and then you have like the program data, and then you have the code on and data Dalvik cache, and then you have this like super long path file name, which is basically where like the optimized DEX sits. On Android 6 and later, you have just like your package directory, and in the package directory you have an APK, and you have the base ODEX file. But in this case, it's actually not an ODEX file, or it's like an ODEX file, but it contains native code. The interesting part is those files are all owned by the system, and they can only be read and written by actually install D and Zygote. So your own app can actually not read its own like binary, which makes this very interesting. Yeah, yeah, because Zygote, like, Zygote just like loads into memory and then executes, so your app doesn't really need to be able to read its own code. So if you go back and look at generic app modification, how does this actually work? Normally you would do something like APK tool, Then you just like unpack the file, modify the Smalley code, and use APK tool to like rebuild the APK. Then you use jar signer to like sign the file, and then you can just like run the modified APK. Of course, in this case, the signature would be broken because you don't have the author's like keys. On the device, APKs are compiled using dex to out. We can just say this is dex file, this is the out file, and then you have the modified APK. So what you do with this odex file, you still have to like patch the modified odex file to be the odex file contains like a CRC32 of the dex file it was generated from. This is not a security check at all. It's just for the VM, so the VM can see, oh, maybe the APK was updated and now the CRC doesn't match the dex file, and just like recompile it. That's just like a pure let's not run old code feature. It's not a security feature. And in order to patch the CRC file, I made a small tool. It's like really tiny, and that's like also open source, where you can just like patch the CRC of the odex file. So what you can do, basically, which will work on any Android version, you can just like you need to override the odex file of the specific app. So if your device is rooted, you can just like go and like override that specific file. And so either in the Dalvik cache or in the app out cache, and then just like stop the app and restart it, and you could just have this modified APK, and it will actually bypass all of the checks because you only modified the code that it's executed, but not the original APK. And then of course you have to like unroot because you want to still pass like the general device integrity checks. So if you go back to if you think back about earlier slides where I said like, oh, on Android 4 you can't really detect if a bootloader is unlocked. That basically means on Android 4 you can trivially bypass app integrity checks, because yeah, if you have a root that is based on an unlocked bootloader, you can just do that. Yeah, so that is bypassed. So, but I was like, yeah, so I bet we can also find other ways to do this. So the main goal for this attack is, like as before, we really want to override this one odex file. But we know only basically two daemons can actually like write, or two binaries actually have the SLinux privileges to write to this file or this class of files, which is install-d and zygote. But who else can write to any file in the file system? Of course, the kernel, the Linux kernel, because access privilege, anything that's like SLinux or file permissions do not exist for the kernel itself. And yeah, 1 year ago, there was this like nice kernel bug by the name of Dirty Cow, which, and for this talk, I just like, yeah, it basically allowed you to like override any file in the file system that you can read. So as a shell user, you can obviously read all odex files. So now we can go and basically, since we can read any odex file without rooting the device, we can actually do this attack without rooting a phone. So basically the same procedure, we APK tool the file, modify the odex file and patch everything. But the one small issue is like Dirty Cow can only overwrite files, but like basically not append like or increase the size of a file. And the one easy trick that I found is, so normally dex2out runs with like processor specific optimizations. As you can see down here, it says like Cortex A53, and optimizations usually make files much bigger. So if you just compile, if you just run dex2out without optimizations, you will actually get a much smaller file. So even if you add like a lot of code to like the patched app, your file will still be smaller, and you can very nicely overwrite the odex file using Dirty Cow. Yeah, I'm actually going to show you, do a little live demo. because it's actually that simple. First, I'm going to show you. So let's see until. Just have to wait a little bit until the camera adjusts to the right. There we go. So this is like this demo app I wrote. Yep, and we pass all of the checks. And so basically unrooted device, unmodified app, looks good. So, is this readable? I think that's okay. That's fine. So there's this this is the APK. So if you just like unpack this APK quickly. And then we're just like gonna modify some code. So this is just like some Smiley code, which I'm gonna just like patch into this application. That's all we need. So, and now we can just now we just like rebuild with basically use APK tool again, and like also sign. Use like the jar signer with like the default key store to like just have a self-signed APK. Oh, I guess I didn't set the path for that. Where is that path? Who knows where that file is? It's in build tools. No, I have the path for jar signer. The command arguments for jar signer. Yeah, that. I guess I should have. Yeah. Where is that? Oh yeah. It's. I heard JDK, so yeah, that's exactly where it is. Where is my JDK? Definitely not here. Where is the JDK? Yeah. Oh, that's already done. There we go. Nope. Should be more of those. Yeah. I was pretty sure. There we go. So let's do this again. Yeah. So now we re-signed the app. So what else do we need to do? So we have our re-signed app. So we want to compile this app on the device with basically we're pushing like the new APK and getting the modified compiled ODEX. Now we want the original. We want the original base file because we need to extract the original CRC. And now we can do, let's say, this is the original one, and this one is the one we want to change. So what we're going to do here is I want to change this one to this one. And now if we run it on this, nope. Yeah, old CRC, new CRC. Oh. Yeah, it's always nice if you forget the command line of your own applications. And now we modify, yeah, now it's modified. So this is like patched. And for the attack, basically we push this modified app, the modified ODEX file to the device and then run dirty cow. It's another nice point of failure in this demo. And it didn't work. I can try again. I have a few more minutes. Yeah, I like live demos. They just like turn to. Sometimes they just like do not work on the first try. It's all good. Okay, let's try this again. So you're just going to reinstall the original APK. Since you already have all the modified files, you can just skip everything else. Okay. So let's try it one more time. And it worked. So let's go to the camera. Let's wait until the white. So, and now you see this nice pop-up we added, and you will see all the checks passing, and so, yeah, and basically, yeah, unrooted device, but complete, basically, app compromised from the integrity level. So, what is the actual impact of this attack? Yeah, it's of course limited to Android devices that's still vulnerable to Dirty Cow. There's probably like a lot of them. The nice part is that basically the owner of the device has to like perform this attack himself, because apps, so like if you get a malicious app that runs on your device, it could not modify another app because apps cannot open ODEX files. So that's good. Of course, the attack goes way beyond SafetyNet attestation. So any device that any check you do on like ODEX files or something will be vulnerable to this attack. The nice part is Android 7 devices will not be vulnerable, because Google changed basically the policy for their CTS tests, so they will actually check if your kernel has this, still has this bug, and then you will not get Google certification for Android 7 devices. The generic attacker told Google like many, I guess, now it's like probably 2 years ago, so they know it, but it's like, I guess, hard to fix. Copperhead OS is like hardened Android clone. They actually, not by accident, by design, mitigate any kind of these attacks by just recompiling every app on every start. So that would kill like modified ODEX files. So I made some observations over time. So basic integrity was like July 2016. Suddenly I like found this, and I was like, hey, does anybody know, because this is not really documented. And then again in, I guess, May this year, they added this advice field that will tell you about like your bootloader, or like please refresh your device because we determined your device was like tampered. So that was like kind of interesting. Now there's also like a mailing list where you can like subscribe, and they will tell you, I guess, about new features, but the website is still will not be updated like in a timely way at all. Also, the little bit more interesting part, so since attestation is based on CTS data, and CTS is run by manufacturers before they release an update or a patch or a phone. So if this data is false or not up to date, of course the CTS test will fail and will tell you like, hey, your device has been modified. And I actually found that on like some Yota phone where like, I guess they rolled out a security patch and did not submit the CTS data. So on all of those patched devices, actually all of this would just fail just because Google didn't have the up-to-date data. And actually Google did it themselves. Here in March this year, Google had to like pull a security update for the Nexus 7 because it like broke their safety net, and thereby also Android Pay part. And it's probably that the last part I don't know like how that happened, but basically if SafetyNet attestation has an outage and you can't react to like this outage, you will have an outage too as like an app developer, and you probably do not want that. The fun part about SafetyNet in general, Google really improves it like all the time. If you like follow forums, routing forums, and so on very closely, you will see this cat and mouse game. And yeah, it's mostly for Google, I guess, mostly about protecting Android Pay. But yeah, I guess the big benefit of SafetyNet and the attestation part is that really you have a bunch of people at Google who constantly like work on improving basically the results for SafetyNet. So if you use that to secure your own app, you get like a lot of security for free, where you otherwise would have to like employ a bunch of people or buy like a third-party product that does like app and device integrity checks for your service. The nice part is attestation is free. But of course, it can go down and have outages. You basically don't get an SLA. There's rate limits which you should never be able to reach. And it's free. It's like if you compare it to like third-party services that are not free, this should be interesting. On a side note about malware, so there's a lot of Android malware that basically is repackaged Android apps. So basically, people just like add their like whatever they want to do to like Angry Birds, and then you will like download that modified Angry Birds. If that game or like that app would actually run SafetyNet, they would basically have to, basically that repackaging wouldn't work because the app would just like say, hey, I was modified and I don't work. So they have to like either cut out a lot of functionality of that specific app, and they probably won't do that because then we'll just like go after some other app. So you can basically use this to basically prevent your product from being targeted by app repackaging malware, as like a side effect. So summary and conclusions. Basically, it's like one of the essential platform security services. And if you're like serious about like any kind of app security on Android, you should really, really use it. As I showed you, there's like some like downsides or some things you have to be aware of, but you have to be aware of those anyway if you roll your own or like buy a third-party service. And the majority of apps will just like benefit from this, and it will really get better over time, and you can really like see Google doing improvements to that. And that's it. Slides are online, tools are online on my GitHub page, or like if you go to mulliner.org/Android, you'll find everything related to this talk. Some more references to read up. That's it. Thank you very much, and I guess we have 2 minutes for questions.
Thank you very much, Colin. We have about 3 minutes for questions. So first of all, I would like to take one question from the internet, please. Oh, and just to mention that people leaving or coming in, please be quiet and give us another 3 minutes of quiet while we do the Q&A.
Why does SafetyNet not run with full permissions?
Because it runs inside the Google Play services, like basically the Play app, like the Android Play app service app, and that only runs as system service, and so it doesn't run with full services because of that it just runs in a slightly privileged app. And I think that's by design. Also think about other manufacturers like maybe Samsung or HTC. They maybe, like other companies probably do not want to have a super high privileged Google process on their phones. No, it's just by design. That's the only thing I can think of. Yeah.
Thank you. Next question from microphone number 2, please.
Hello. Can you hear me? Yeah. Thank you for your talk, first of all. It looks like SafetyNet runs under system user, right?
Yeah.
And it has way more privileges to check for file system than ordinary application.
Yes.
Do you think it is still worth to do enough checks for things like root detect, root of device, and so on?
I think that it really depends on your risk model. If you're very concerned about modified apps or modified devices, of course it makes sense to add your own checks in addition. But I think if you're starting to develop a new app, you should first implement SafetyNet, Attestation, and get all of this right, and then you can start investing money to build your own. Because if you start rolling your own, basically you have to have a team that constantly keeps up to date with Android versions. Because if something changes in your app and your own detection has false positives, you will just disable your app for a lot of people. So yeah, it's depending on what you want to do and how much you want to spend on that.
Thank you very much. Unfortunately, time is up by now, so whoever else has questions, please find Colin after the talk. I know, you probably all know that it's pretty nerve-wracking when you're on stage and your demo or whatever you were planning in your presentation doesn't work as planned. So I hope that you're going to show a lot of empathy and give Colin another big round of applause. Thank you very much.